Our next speaker is Mr. Satya Srinivas B. He is currently working as application specialist in Zeiss India Private Limited, Bengaluru. He has done his MSc in physics from Andhra University, MTech in nanotechnology from NIT Bhopal, and he is currently pursuing his PhD from IIT Hyderabad, Department of Physics in MEMS and Micro Nano Systems Laboratory. His professional experience, as he has worked for more than 10 years in handling surface characterization tools like SEM, AFM, surface profilers, and sample preparation tools. He has worked in Shell Technology Center, Bangalore as an experimentalist. And prior to Shell, he has worked as a technical and application support manager for Hitachi Electron Microscope and Bruker Atomic Force Microscope distributor in India. So far in his career, he has handled multiple projects, namely Green Hydrogen Project and Materials and Corrosion Project, Characterization Lab equipped with AFM and SEM, Surface Profilers, Contact and Non-Contact, Field Electron Scanning Electron Microscope, and Sample Preparation Tools. So I welcome Satya sir to deliver his lecture on advances in FESEM technology and its applications today. Sir, please.
Yes. Thank you so much, ma'am. Thank you for your brief introduction. So my agenda goes like this. So I'll just quickly introduce the Zeiss electron Zeiss, what Zeiss is, and what is the Zeiss portfolio, product portfolio, what we have particularly for this microscopy division, and then with that, what are the unique strengths of Zeiss? I try to give some info on that. And then later I'll move to the scanning electron microscopy applications, where you can see the same system, the versatility, the nature, the different type of samples you can handle because of the technology developments in electron microscopy, where it supports all the departments starting from biological to materials and metallurgy. Why I'm saying like that is from very soft samples to very hard samples, which can sustain the electron beam, higher electron beam kV, higher kV electron beams also. So with that you can use the same system for the imaging as well as the analytical applications. So we'll discuss few applications and then move to basics of scanning electron microscope, because after discussing all those high-end applications, just a quick overview what we were talking about, the information saying topography, morphology, some different words. So what exactly is that, and how the system is capable of picking up those signals and forming the image. A few slides on that, and then later I'll take you to the in situ applications in scanning electron microscopy, where you can add different type of stages, cooling stages, tensile stages, heating stages, even atomic force microscopy, Raman combined with scanning electron microscopy. A couple of images on that, and we'll discuss. So this is what the overview of my agenda. So okay, so this slides talks about the complete product portfolio of the Zeiss, particularly in the microscopy division. You can see the different products starting from. Let me change my pointer to this. So yeah, here you can see we have the electron mic. We handle Zeiss manufacturers the products which can resolve features of 1 micron or to a sub-nanometer level. So we handle a complete product portfolio where you can see a micro to complete sub-nanometer scale resolution images. So here first, if you come about the stereo microscopy, and then we in the light microscopy section, we have a different segments: stereo microscope, polarized, confocal, and all these comes under light microscopy division. Whereas the topic what we are talking today is the field emission scanning electron microscopy, where you can comfortably achieve the less than nanometer resolution. After these presentation slides, we will practice. I'll try to demonstrate the system online so that you can feel the resolution, like how quickly we can move from a few micron to the micro scale imaging to the nano scale, sub nanometer scale imaging on a couple of samples. Like a standard sample what we have is a gold on carbon, and few biological samples also I try to demonstrate. Nowadays the recent technology, like where you without any changing the sample surface without, which is called a non-destructive technique. You can pick up a complete information, complete volume information, and you can generate a 3D volume, and then you can understand the deeply buried structures with a nanoscale XRM. Previously also this type of technology is available, but the resolution is completely limited during that time. But now the technology development helps to get a complete field less than a 50 nanometer on a particular block. You can without any sample destruction, you can pick up the complete 3D volume information through XRMs. So these are the three segments: light microscopy and electron microscopy, and then X-ray microscopy. So all these products are handled by the Carl Zeiss. So we know what are the constraints when you are using a particular instrument, and what are to be developed for further any of the research. So we work closely with all the fields, which helps us to improve our product and their capabilities. One more important point is having such a large portfolio. We even can the technique called as a correlative microscopy, which helps all information, like whatever you pick up in the micro scale, and the same sample with a particular holder, you can transfer that to electron microscope, and then you can reach that area of interest, and quickly you can move to higher magnification. So what I mean to say is, when you want to study a particular unknown surface with a different feature, and you are interested in a particular micron feature, and then quickly you want to do the analysis at nanoscale, if you disturb the sample to one system to another system, definitely reaching that 1 micron feature itself is very difficult in any of the microscopy. But whereas having these correlative microscopy concept, you can bring the stage directly from any of the light microscopy, Carl Zeiss light microscopy, to any of the field emission system, and with the coordinates of the particular particular area of interest, ROI or AOI, then quickly you can reach that, and quickly you can magnify. So that is one of the strength having these handling this complete portfolio. So quickly, now the interested topic is the field emission scanning electron microscopy. In the field emission scanning electron microscopy also, how the development happened, like initially when the scanning electron microscope is introduced in the field. So the first time we introduced these electromagnetic and electrostatic lenses almost 20 years back. Now all the manufacturers are trying to copy and prepare similar thing, because with this technology only you can able to handle a different type of samples. So particularly even including the magnetic samples you can handle when you have such a technology. So gradually when the development happened, like in the variable pressure mode was introduced in the next generation, where you can handle a beam sensitive samples, non-conducting samples through a variable pressure method. We will discuss this, what are the methods to handle the non-conducting samples and how we can do, because most of them very initial stages, people think that the only conducting samples are allowed in electron microscopy. For non-conducting we cannot do, because the source or the beam what we are using is an electron beam. So later on the variable pressure mode, where you introduce some gas molecules inside the chamber and try to avoid the charging effect, and then you can pick up the surface information of those beam sensitive samples through variable pressure mode, is introduced in the year of 2000. So which allows even non-conducting samples also can be analyzed through electron microscopy. Later, gradually the resolution at lower KVs with our Gemini technology is much improved, and then now we can achieve comfortably sub-nanometer resolution through our Gemini series system. So with this, the development happened in all the samples handling, which is called as a more sample flexibility, particularly non-conducting samples, beam sensitive sample, and the resolution part also much better. So improved in the recent Gemini systems, and there are particular workflows. So these systems are not only for imaging, right? You can do you can attach a lot of analytical tools, particularly like EDS, EBSD, and all other analytical tools. There, if you want to study a particular application with a particular workflow, there are dedicated workflows, automated workflows are available, where there is a very nominal contribution from the operator. The system itself can perform all the instructions with that workflows. So this is what the technology development, particularly in the field emission segment. The later topics we will discuss what are the additional attachments presently included in these for field emission scanning electron microscope. So this is what the introduction I want to give about this Zeiss product portfolio and the particularly field emission strengths, how exactly the technology development happened. And then few applications. When we talk about a few applications, these slides are particularly for those who want to understand why exactly these electron microscopy, in which areas these are useful. So please try to compare these results or try to understand these output, whatever the outputs I'm showing, with the area of research where you are performing and how best you can use this SEM. You yourself can understand easily, and then you can come out with any of the question. So the same electron microscopy, the field emission scanning electron microscope, or any conventional SEM scanning electron microscope, there are different types of microscopes based on the source what we use over there. So these are all used for high quality imaging, particularly a nanoscale imaging, and then not only nanoscale, high resolution imaging. These are useful to understand the failure analysis. If you are working on particularly on any failure analysis, the field broken samples or testing sample, looking at the surface features, using a different detectors, you can easily identify, you can easily understand the failure region, and with that features you can clearly define what exactly the type of failure, and then from that you can go back to the process procedure, whatever the manufacturing process, and fix those issues in the manufacturing process. And apart from that failure analysis, even surface analysis studies for very beam sensitive samples. So for example, this is an electrode which is in a battery. So after a particular cycles of usage, you want to see how exactly the degradation happened on the because this is what defines the efficiency of the batteries, right? So these electrodes and all those things. So you can know how after particular cycles you can know the surface degradation, what exactly the contamination or deposition on any of the catalyst material or the anode or electrode, these electrodes, right? So those in that particular surface information, this is one of the typical samples, which is battery separator, which is a battery separator or which completely insulator. So you cannot use a higher KVs for such type of samples, but still you can do the analysis using these electron microscopy at very lower KVs. So cross-sectional understandings. Once you do the coatings, multiple coatings on any sample surface, if you want to see the cross section of the thickness of the film, or how exactly those are connected or attached, or the adhesiveness of the layer to the base material, any air gaps presented over after the coating material, or some anodizing layers. So these are all the applications when you come for cross-sectional analysis. So these are all high resolution imaging part of it. When you want to compare, when you come to understand the grain analysis and the orientation, the analytical tools attached to these systems like EBSD can give you much more information on the crystalline nature and the grain information, grain orientation. So this is also one of the application area for electron microscopy. For those who are working in a semiconductor industry, or who are working with semiconductor samples, and they want to understand the electrical characterization after doing some of the pattern generations on those lithographies. For such applications also you can use the scanning electron microscopy. Finally, after doing the analysis, after picking up the high resolution imaging, if you want to measure each and every part of these one for metrology, measurements in metrology, you will get the basic software to do the two-dimensional measurements. And if you want to go for a volume measurements and additional measurements, there are typical softwares available to perform to measure all those things. So from failure analysis to measurements in metrology, the same system you can use for various applications. That is why the system is completely versatile, and the capabilities, whatever we talk, the capabilities, all this comes because of the column strength, the design of the column, which the Zeiss has its unique nature, in that unique design in that, so that it can allow very hard samples, which can allow the samples which can sustain 30 kV, and even you can image those samples which are not cannot take the accelerating voltage around 100 volts or 200 volts. Even lesser than that, we call as ultra low imaging. You can perform the analysis at 100 volts and get a high resolution in that. So these are few areas of applications for particularly electron microscopy. For few areas, there are many other areas also which have been mentioned here. A few examples like the heating stage, like some lithography technique where you can do the patterning on a substrate on the substrate. So there are many other applications as well. Few examples we will see, and try to understand how exactly this electron microscope is able to give some more information on the characterization of such sample. These images, you can see the application in the battery research, which I already talked in the first slide. So in this, you can see the cathode particles with very high resolution. You can understand the cathode particles, and size of these grains can tell you the information about which type of catalyst particles are used, and with this size, once you do the cross section of this and understand after particular cycles aging of the battery, people say, and then during that time you can clearly understand if you are doing some reverse engineering and you want to understand which type of cathode particles are used. So with the size of grain size, you can clearly come to an understanding of the type of the particles there. This is the cross section view of the battery, where we are concentrated particularly on this battery separator material. So with the anode and cathode, there is in between there is a battery separator, where the pore size of the battery separator defines the ionic conductivity. So understanding those pore size or the surface information is much important, which definitely gives an idea or how exactly the ion conductancy, understanding the rate of transfer of those ion conductance. So if you get a clear understanding of those pores, if you apply a particular higher KVs, particularly such samples, the pores start what you call the surface degradation happens, and you don't get actual information. But with the field emission scanning electron microscope technique, with a lower low kV information, even you can resolve such surface beam sensitive features. And one more example of the cathode particle, understanding the shape and size is one part, and understanding the deposition on the particles, what exactly after particular cycles, how these cathode particles are deposited by, because maybe the ionomers, maybe the binders, or some of the materials when they is in its working condition, or when it is when these electrodes are combined, and the particular after few cycles, right? So these informations, particularly what I meant to say is not only for the just a clear high resolution imaging, you can understand the surface information, measure the porosity, measure the size of those pores, understand the deposition on a particle, and how exactly the efficiency related to these deposition surface information of those particles also, it's very clear on that. And few more examples on the same area. You can see the binders, which are completely charges, like when you do the SEM analysis, this information, understanding this information, whether the binders are completely covers the battery separator material, or if you are doing a lot of binder, if you are using, then again how exactly the efficient, the same principles, particularly either maybe in a fuel cell or maybe in a battery, these hydrogen splitting, all these are common: electrode, anode, cathode, battery separator, or a separator, or ionomer binder. So understanding the distribution of these binders also gives you an idea how exactly the bar coating or the coating happened on the electrodes. This is what the few like images on the battery research side. So now we'll move to the polymer applications. People may be working on the polymers, and they know how sensitive they are for electron beam. So when you apply a particular higher kV for any of the polymers, then you definitely will see there is a huge charging effect, and you are not able to understand any information, or you are not able to measure any width or the diameter of those polymers, or the surface features on the polymer surface. But at very lower kV, with a lower kV technology, very clearly you can understand the surface, and the depth of penetration, you can see the depth of focus here is much more in field emission scanning electron microscope. When you are trying to focus particular part, the other fibers which are underneath the particular fiber are also under focus, right? So that is what you will get a particular help from compared to the normal optical microscope or a basic conventional SEM. The depth of focus is much higher in the field emission source, which helps you to understand more surface in more information if there are freely suspended features are there, because one end of this fiber is suspended here, but other ends it is not suspended, but still you are able to resolve clearly the surface information. Few more on the examples on the phase screen, where we can use the cryo attachment to the system, where you can cool down the sample surface, because sometimes if you dry the sample, if you are bringing it to normal atmospheric conditions, the surface features may vary. So for such applications, if you want to do the analysis, there is an attachment called as a cooling stage, or if you want to go for further lower temperature range, then you can come down to the cryo stage, so where you can freeze the sample to a particular temperature and then maintain its natural condition, and you can pick up the surface information. So these are all of various applications, particularly in the polymer side. So few more examples in the ceramics, where these are all completely non-conducting samples, but the charging effect, the contrast imaging, all these things, if you see this nanometer scale, whatever the scale I'm talking is at 100 nanometers. So at 100 nanometer, almost more than 1 lakh or 1.5 lakh magnification, the surface feature, the facets of this alumina nanosphere, you can very clearly see, right? So that is the strength of the field emission source. Because these are all non-conducting samples. If you apply higher kV, as you know, higher the kV, better the resolution, right? But if you apply higher kVs for such samples, it is very difficult to focus very difficult to get these images. So the system should be capable of picking up a higher resolution at lower kVs. So this is one of the best example for such the low kV application. And these are here you can see the contrast difference, right? The contrast difference itself through the electron microscopy, even with the imaging, which is called as material contrast. So through backscattered electron imaging, you can even pick up the contrast with respect to the material contrast. What I mean to say is, for example, if any low Z material, which is particularly any polymer matrix, where you introduce some nanoparticles, conductive nanoparticle, and if you want to understand the distribution of those nanoparticles and in any polymer matrix, then definitely these backscattered picking up the energy selective backscattered signal through these particular detector, you can understand the distribution of those metal particles even in the polymer matrix. So with the image itself, you can clearly understand how the distribution of this nanoparticle, which is this low Z material, which is a higher atomic number material, which is called as a material contrast. So if you go further in depth in the contrast, so the topography contrast, voltage contrast, electron channeling contrast imaging, or material contrast imaging, these are all diverse applications. Even understanding the sample, understanding the sample more in depth with the imaging itself. Yes, anyhow, you have this EDS technique, like energy dispersive technique, for understanding the material distribution, or particularly understanding the elemental composition present over there. Even at lower kVs nowadays, the technology you have is like even with at a very low kVs, because samples cannot sustain the higher kV, and if you want to get EDS signal, then you need to apply higher kVs, like more than 15 kV. This is what the understanding people has. But now with this latest technologies, even with the lower kV also, even with lower kV like 5 kV, 2 kV, you can generate you can pick up the EDS signal, and you can have the identification of those elements wherever it is present. But the sample preparation for such type of things are a little bit typical. You can clearly see where the distribution, the mapping of those all individual elements at very low kV. right? So there are different detectors, like in the EDS you have a windowless detectors, or you have a very high sensitive detectors to confirm these elements. Few more application areas like aerospace engineering, you can see you can see few applications like the coating, how exactly the coating remains, or is there any peel off of these coatings analysis you can perform. And this is what I was talking about, the material contrast. Here you can see the different contrast in the image itself. So the darker if you have the dark spots which are low Z material, from the image itself we can understand whether it is a corrosion, or it is something a low G material on any particular alloy. So you can clearly understand the surface features at a very high resolution. Even you can understand the material distribution in a particular alloy, right? So these are few applications in aerospace engineering. A few more applications in automobile industry, the surface features, inclusions, phosphate coating, where you can understand the grain size of the grains, and the failure, if the failure analysis, if you are doing the initiation of the crack and how it exactly penetrates, and the direction of these cracks through the features. If you go for a higher magnification, understand the microstructures, right? There you can clearly distinguish or separate these features from the normal surface. So automobile industry, these are the few examples. And once you are able to identify some particles on any of the filter paper, so where people in the technical cleanliness application people use, they will filter out all the contamination or the additional particles come out after washing the particular part, and then they pass those through the filter paper and want to identify these particular elements. So there are particular softwares where the whole filter paper can be analyzed, individual particles can be picked up, and the analysis, not only the elemental analysis, the volume, the area, all those can be calculated and tabulated with a minimal interruption from any of the operator. So such a type of applications and workflows also possible. Few more examples on the electronic side. So the shoulder bombs and the cross sections of ICs. So how exactly the layer thickness, that information you can understand when you are doing any cross section application. The shoulder bumps, how exactly the shape and size, a few more the images you can see, right? So from the electrical spring, because here also you can see because of the depth of focus in the concept depth of focus in the electron microscopy, you are very clearly observing these surface area as well as this and the some, because of the contrast in the material, or because of the various detection technology you can see very clearly there are block spots. And then if you go for elemental analysis on this particular thing, you can clearly understand from where it happens, or whether it is any contamination, or it may cause something else. So that understanding even these images can give you. These are all examples where with the image itself you can understand more about the product. So these are all in the medical technology, medical implants. You can see how the coatings on the how the coating surface looks like. These are all helps you to understand the surface topography information of particular product, right? So few more examples with EDS. Yeah, this is one example where regular day-to-day life you will see the coating thickness of the tablets. So there are the tablets where you have a multiple coatings on that. So this coating thickness only defines the dilution time. That is why whenever you take some medicine, the particular time gap, whenever the doctor suggests you to go for take the medicine after 10 minutes, 15 minutes of after taking this food or before. So that's what all this depends on, this thickness of the coatings. So the nowadays this is mandatory for the many of the pharma industry follow this electron microscopy imaging technique for understanding the coating thickness, and how exactly the thickness over a coating, how many layers are present over there. These layers you can clearly distinguish these layers, right? That is because of the voltage contrast imaging, material contrast imaging through the backscattered electron detector. Few more examples on the biological side. So human hair also one of the people who works in the who are doing cosmetic, shampoo, all those things, they do use this electron microscopy for characterization and understanding the surface after applying a particular concentration, and then see how the surface changes. And one more beautiful example of this mosquito eye. You can see the mosquito eye, very sensitive sample, but without any sample degradation, you can clearly understand the surface features, right? So these are few examples in biological sciences, and these are all in textile industry. How exactly people if they want to strengthen this textile, or they coat with some nanoparticles. So if you want to understand those particles presence through the topography detector, through the backscatter detector, which I'm going to say is if you want to understand the topography information or the distribution of those particles, so very clearly you can understand the surface features through different detection suite in the electron microscopy. The final, I think the area which is food and beverages, you can see the rice grain, surface of the rice grain, how exactly the salt crystals. These are the few examples in food and beverages. From this, what I want to convey the message is the same electron microscopy with the unique capability, with the unique techniques. The same system can be used for multiple different type of areas. With this, the system is much more versatile. You can have a lot of flexibility on the sample side. This is not for all the manufacturers. This is something special for the Carl Zeiss, where we have a complete technology for this performing the low kV, higher kV, handling the beam sensitive sample with the different detection systems. So if we go in detail, we can discuss how exactly we are able to pick up such a beam sensitive information at higher resolutions with a very low kV. So that all depends on the system design, system strength, and system unique patented technologies. So it is not such easy directly you can keeping the sample and you cannot pick up. There are some parameters have to understand to analyze all the samples in a single system. So these are the main areas where people can use these electron microscopy. Yeah, this is a very basic to understand the SEM, what exactly SC, what exactly BSC, how you are able to get a topography information by SC signal, what exactly the backscatter electron detector, which defines some morphology information. The EDS, whatever we are talking, right? EDS, how the EDS works. This interaction volume defines all the signals which are coming out, and we are picking with the dedicated detectors. So this is a signal, and this one is the BSC signal, and the photon released because of the electron jumping from higher energy to lower energy level is what the EDS detector will pick up, and which has a complete footprint of that element, and it will give you what exactly the elements over there. So these are the source what we use. There are two different type of sources, tungsten and LAB source in the conventional SEM, whereas in the field emission source you have these the thermionic emission and cold fix. Most of the system for analytical applications and the high resolution imaging, you can go for the Schottky systems. So the main difference between these conventional and SEM, which you have to understand, like if you are having a particles of a few tens of nanometer, and if you are trying to resolve those things in a conventional SEM, it is a little bit difficult, because the energy spread over here is much more higher, whereas in the field emission source the energy spread is more concentrated, so you will get a high resolution imaging in the field emission. So depending on the sample feature, depending on the application what you are looking for, you have to select a suitable system for that. So other additional in situ applications what we are talking about, other than the imaging, the crystalline information, the elemental understanding of the elements present over there, or the grains, orientation of these grains, and all such information through these additional attachments you can get it. EDS, WDS, the wavelength dispersive spectroscopy is much more accurate, but the interpretation of the data, picking up the data, collection of the data is much complicated compared to the EDS. So EBSD is also for the EBSD is for understanding the crystalline, the complete the what you call the crystalline information of the sample, and then you can understand the inverse pole figures and all such information. Cathode load luminescence, which is also one of the additional attachment for optical property, particularly for geoscience people, they use these things. So the other than the imaging, EDS and EBSD, even you can have the few applications we already discussed. where you can get the particle size, morphology, and even the material contrast. You can see here the material contrast, dark and bright areas, where you can understand which the polymer band, which the low Z material is, which is the higher atomic number. This is one of the typical applications which I am talking about, the crystal structure. With the BSCD information itself, you can identify the dislocations, defects, or the grain orientations. This is what I was talking about, electron channeling contrast imaging, which is one of the advanced application in field emission scanning electron microscopy. And apart from these detectors, even you can attach the atomic force microscopy also for in the scanning electron microscopy chamber, to understand even further go down to the resolution and understand some few properties, particularly AFM, you know, right? The other than the imaging, you can go for optical property, you can go for electrical properties, magnetic properties. Such information you can pick up through AFM. And even the tensile stages, compression stage, all these stages you can attach to understand the strength of these samples. You can apply some tensile load on the sample, and how exactly the grain boundaries changes when you through the imaging you can do. These are all the in situ characterization technique. These are additional attachments. The recent development in the field emission scanning electron microscope is if you want to study some information which are deep inside the sample surface. It is not on the sample surface, it is inside which are deeply buried structures. If you want to see, you have an additional attachment called laser attachment. Previously people used to do with the crossbeam, where you can apply additional gallium source and you can remove the surface. But if the surface feature, whatever the area of interest is inside the sample, it will be deeper inside, then removing through the gallium source is difficult, time consuming, and also the source is too costly. So we can remove through the laser. So first of all, it will identify the exact, it will read in the scanning electron microscope, you exactly read the position of the area of interest through these fiducial markers, and first you will recognize where exactly these coordinates and how much depth you have to remove. Then you will bring this sample to this laser chamber, where you can remove the sample, where you can remove the surface, and you can reach exactly the area of interest which is inside. So if the defects are penetrating, if some area of interest is inside the surface, you can remove through the laser source very quickly. And then further again with the correlative technique, with the same sample, with the same area, without losing the area of interest, you can bring back to the SEM chamber, and you can image those things. So if further, if there any deposition because of the laser or any debris present over there, you can further fine tune, you can further fine mill it with the gallium source, and you can clearly resolve those features inside the sample, right? So you can these information, if you want to pick up, very difficult to do with a mechanical polishing, because the precision is too poor in the mechanical polishing, and the sample size will be too big. But whereas in the small features, such small feature, you can clearly do with these laser workflow. So these are all the advancements happened in the developments happened in the field emission scanning electron microscopy. So these are all used as a more information you can pick up than the only imaging or surface imaging. You can go for EDS, EPS, DEDS, WDS, cathodoluminescence, or a crossbeam for milling the surface, or a laser to remove much more increase the faster rate and go for a deeply buried structure. So these are all advanced technologies in field emission. So with this, I just want to summarize. So what are the existing in situ attachments, as well as the workflows for Zeiss microscopy, apart from these imaging and analytics. So you already saw this imaging plus EBSD, or any surface sensitive imaging, channel contrasting with ECA, and STEM detection also we discussed, in variable pressure method for non-conducting sample. These are all used for imaging and analytics. So if you want to attach some additional information, attach some additional attachments like in situ AFM for particularly magnetic, mechanical, thermal, electrical application, you can attach, and simultaneously you can pick up the data, as well as the heating and cooling and cryo microscopy you can attach for biological samples, or or if you want to see surface modifications at a particular temperature. And probing, these are for semiconductor industry. You can apply some voltage and you can check. Then the tensile for particularly mechanical applications, you can have some indentation also inside this and see the surface information. And the workflows, we already saw some the laser workflow. Similarly, if you want to generate a complete 3D tomography, you can perform through these workflows with a minimal intervention of any of the operation of the person in that. So mineralogy is also possible, which is completely a different topic. But with this EM attached with these mineralogic softwares and particular EDS, you can do the mineralogy, identify all those minerals which are you can segment them and you can do those things. These are the workflows present. These are the additional attachments for in situ application, and these are the very common imaging as well as the analytics area. So these are all wide area. You can cover wide area applications. That's how this is what the SEM. You can see the versatile nature of SEM and in different area. So now we will move to the live demonstration of the system. You can ask if you have any questions, I can answer, and then we'll move to live demonstration.